Let's start again. The title of the lecture is Solving Equations, and I'm going to explain why by using this example. So this is a building that is in fact that I would like to model. And we can see here all the elements that we have already discussed. So on the one hand, we are going to write the energy balance of the building, which depends on the external temperature. We know, and we can see that here there are variations of the external temperature. So you can see here two curves. So the first one is really the variation of the temperature. And then the black one that is here, I will explain the other one another day. So the black one is what we named a load curve, is in fact representing the frequency during which we see a given temperature, or during which the temperature is above a given value. Okay, so this is a load duration curve here. And the same for the irradiation. So we know that we receive sun, that the sun is not constant. So we can see this is a yearly variation of the solar irradiation. And of course, normally we should see zero every day. So it's just a question of details in the plots. And we have also the same kind of duration curve. So how many days or how many hours do we have more than, for example, here 800 watt per square meter of irradiation? Okay, and officially this curve has to be available for a given building. Okay, and it means that it's not only the solar irradiation that is in the middle of the Lemon Lake, so without any shades. Okay, in reality, we have to take into account the shadings that could apply as well. Then we will have to look at the gains from the appliance, so how we use the different elements that we have in the system. So the computer, the computers here, the production of food in the restaurant, etc. And then the production of the light that is consuming electricity and releasing heat. The people who are releasing on the one hand heat, but at the same time release water and carbon dioxide in the atmosphere. And then we will have to understand the role of the air, that is that it needs to be removed and renewed, plus the one that is infiltrated by leakage. We will have to consider the amount of irradiation that we receive, the net amount that we receive from this solar irradiation. Okay. We will also have to look at how much hot water we need. And then we will have also to consider the fact that the buildings are well or not well isolated, which means they will release heat by losses with the environment. So now I have identified each one of the elements in the system. Now I have to make models to try to identify what it means. And the consequence is that if I have to quantify the gains by the appliance, I need to know what is the profile of the electricity consumption in the appliance. And this most probably I can measure. At least I can measure the sum of what is in the lighting system and what is in the list of appliances. The amount of heat that is released by the people is requires to have a profile of the presence of the people as a function of the time that I can then multiply by the mean heat that is delivered by our body. Okay? And for this, typically those values are coming from norms, so the people, the SCR, so the Société des ingénieurs et des architectes Suisse, is giving recommendations on how much a student that is falling asleep in lecture is going to radiate, as well as how much a very active one is going to radiate. And then there are even norms that will say that 25% are sleeping and the rest are really active. So there are a lot of norms that allows you to have those values. The sun, you can have the irradiation that is here, and then you have to calculate the amount of the irradiation that is going to enter the building. This is a priori a function of the window, the glass area, and therefore we are going to represent it with a coefficient, which is a fraction of the solar irradiation that is going to define the gains by the sun. For the ventilation, in fact, what I need is to know what is the flow of the ventilation, and then the heat to be supplied is in fact the difference between the temperature that I need inside and the outside temperature if I have not made any heat recovery. So if I have made heat recovery, then the temperature that will be here will in fact be the temperature at the outlet of the heat recovery heat exchanger. But let's first consider that there is no heat recovery heat exchanger, which means that now by this formula I will be, if I know the flow of air, and the flow of air is typically defined by saying that the volume of air needs to be replaced a certain amount of times per hour. Okay, and this depends now in EPFL. If you are in a lecture room like this, where I guess the renewal rate will be once an hour, while in the labs where you have the possibility of having chemicals that are evaporated, etc. In this case, the renewal rate is much higher, so up to 10. Okay. So, but as soon as I know this value here, I know the CP of air, I know the external temperature that is measured, and I know the temperature that is expected, so I can calculate the amount of heat that is needed by the ventilation, the air renewal. And then I will have also, if I know the quality of the walls and the surface of the walls, then I will be able to calculate the amount of losses by radiation through the wall, which is proportional to the temperature difference between the inside temperature and the outside temperature. Okay? And when I have made the list of all those elements, I know that some are positive and some are negative. And there is an additional one that is positive, which is the amount of heat that is supplied by the distribution system. Which means that now I can calculate how much heat will be needed at a given time of the operation by making the balance. So I have what needs to be compensated minus the gains inside the system. And of course, the amount of heat to be supplied has to be positive. Okay, I will not heat if the gains allows me to reach a temperature which is the comfort temperature. If I'm above the comfort temperature, so officially the heat to be supplied will be negative, which means that it becomes cooling loads. Okay. But I must admit that in this case, the cooling load will come with another comfort temperature. So it means that we will be happy in a room that is between 21 ideally, or 21, and 26. Above 26, we are going to say, okay, it would be nice to have air conditioning. And in between, there is no need to heat and there is no need to cool. Okay? But it means that now I have a formula that allows me to calculate how much heat I need to supply by this building. Okay, so now we are happy because we have the formula. The only thing is that you can see that it would require all the walls characteristics, the surfaces here, and even the part of the walls that are in glass and the part that are with isolation, for example. We need also to have the flow of the ventilation system, which is not so easy, and I need also to identify what is the K, the fraction of the solar irradiation that creates gains inside the system. And this depends also on the area of the windows and the quality of the windows. So the formula is already quite nice, but then we have said, okay, but can we use measurements? And something which is very difficult is to measure the instantaneous, so the heat load in terms of power. Okay? Because there are a lot of things that is going to happen, and of course we are not really interested in having exactly 21 degrees C. It can be 21 plus or minus something. So it means that when you are going to measure the heat load of a building, in fact, you are not going to measure what is happening at a given time, but you are going to measure an integral. So what is the amount of heat that is supplied to the building from a given time to another time? A week, a month, a year. Okay? And this is just an integral, so it means that I will have to make the integral of the amount of heat that is needed. And now what I have done here is that I have looked at the formula, and I can realize that at the end I have one driving force, which is the difference between the comfort temperature and the external temperature, and another driving force which is or unknown, which is coming from the irradiation. So if I want to simplify my formula and use the measurements that I will have, I'm going to write the heat load as being a function of the temperature of the comfort minus the outside temperature, multiplied by a given parameter that I'm going to name kth for the thermal load, minus the gains coming from the irradiation, and this k here is the fraction of the irradiation that is defining the gains from the sun, plus a combination of gains, which are the appliance, the lights, the men, the people in the system who are going to give me the profiles of energy consumption, and they will also, or energy supply in form of heat, and they will also give me the profile of the electricity consumption. Okay? So it's important to make the link between the two, as nothing is going to be lost. And at the end, I will write this at a given time, and then I'm going to make the integral over the time to have the amount of heat that is needed, that is supplied to the building. Okay, so this is the model of the amount of heat that the distribution system has to supply. So now if I'm looking at this, and I want to have measurements, so what we can say, for example, is that let's look in the past and look at the amount of heat that has been consumed by a given building. Okay, and I'm going to give you two values. So I have a measurement from January to December, so the whole year. And this gives you Q1. It's an amount of energy in kilowatt hour that has been supplied in the building. And I give you another one from February to March, and that gives you Q2. And what I would like you to do now is to calculate what is the value of two unknowns. Because in fact, the gains can be approximated. And there, if I can approximate the gains, so it means the electricity consumption in the building, in fact, plus the presence of the people, then there are two unknowns. The fraction of the irradiation that creates gains inside the building, and the coefficient that is multiplying the temperature difference here. So temperature difference means that this coefficient here includes the ventilation part and the quality of the walls, okay, and the types of the walls, okay? So what I would like you to do is to try to solve this problem, which is calculate the value of Kson and Kth in such a way that the heat load that is supplied over the year is equal to Q1, and the heat load that is supplied from February to March is equal to Q2. Two equations, two unknowns. Okay? With one difficulty here is that the equation is very special because of the max that is here. Okay? It means that it's not so easy to solve in an analytical way. Okay? So what I'm going now to discuss is how do we solve this kind of problem. So a set of equations that depends on a set of variables and the set of equations has to be set to 0 by identifying the value of the variables. So this is one type of problem. So this is the first problem that you will have to solve, but you have to know that this will be question that you will be facing a lot of time. So for example, what is the value of the temperature if I give you the value of the enthalpy? As soon as the enthalpy is a nonlinear function of the temperature, so the Cp is not always a constant, but it can be a polynomial, then you will have to solve one equation that is going to give you what is the value what is the value of the temperature if for a given enthalpy or for a given entropy. Okay, so those are questions that you will have to solve, for example. In reality, those equations can be formulated in with two types: the implicit form and the explicit form. The implicit form is find x for a given, so that the function of x is equal to 0. And the explicit form is that x is a function of x, of f of x. Okay? So calculate the value of x such that the value of the function is equal to x. But the function depends on x. Okay? So those are two different forms of equations, so the implicit and the explicit one. This can be expressed in one dimension, so one equation is going to solve the value of one, fix the value of one variable. Or we can have a set of equations to be solved to find a set of values of variables. So it means find the value of a vector in such a way that the vector of the functions is equal to 0. Okay? And in this case, there are also two forms, the implicit one or the explicit scheme. Okay, so how do we solve this problem? So the question is, how do we find the value of x in such a way that f of x is equal to 0? As you have made a lot of mathematics to arrive in your master, you know that there is a magic formula. So it's the Taylor approximation. I can always approximate a function by the Taylor development, which is going to tell me that the function is, the value of a function is equal to the value of a function at a given point, plus the variations times the derivative, plus the second dimension of variations times the second derivative. And if I'm going to the infinite, the function is represented by this polynomial. Okay? In a case, so I'm going to use this in order to solve my problem. And I'm going to say, okay, if my function is approximated by a sum of terms, so it can be represented by a polynomial, what I can do is that I can say, okay, let's assume that at a given point, I can represent the function by its first order. And in this case, the function is becoming f, which is f0. f for given approximation of x, plus the variation of x times the derivative of f of x. Okay, at x0. Okay, and I know that this approximation, I'm going to say, okay, but I'm going to consider this as being an approximation of the function, and I need to find the zero. So let's solve this, and let's calculate the value of x. So x0 is not known, the f of x0 is known. The only thing that is unknown is x star here. Okay. So now if I want this function to be set to 0, then I can calculate a new value of x that is the previous value of x minus the ratio between the function of x and its derivative, which can then be generalized by iterations in this way. Okay? Which allows me to have an algorithm to solve the problem. So now I'm going to guess a value of x. I'm going to calculate to do the Taylor development, meaning that I'm going to calculate the first derivative, so I limit to the first order. Knowing the first derivative, I'm going to calculate the new value of x, and I'm going to recalculate the value of x as soon as I do not move anymore. When I'm saying do not move anymore, it means that the f of x is sufficiently close to 0. So this is a numerical method. So it means that the reaching 0 needs to be tested. Okay? So what does it mean? It means that if I am at a given point, I can calculate the value of the function. So I'm looking for this value here, which is the value at which the function is equal to 0. Okay? So what I'm going to do, and of course I'm making the assumption that I will not make the plot, because I do not, if I have to make the plot, I need to calculate a lot of times the function. Okay? So I'm going to do it with a minimum number of calculations. So I'm starting in this point, I'm calculating the derivatives, and I'm going to say that the next point will be xn plus 1 by solving this equation. So the slope is giving me is defining a straight line, and the point here, the f0, defines the location of the straight line, like the slope and the location. Okay, and then I can calculate the new value and continue like this until I'm sufficiently close from the solution. One of the elements there is that I need to calculate the slope. So how do I calculate the slope? I have two different ways. I can calculate the slope by making perturbations. So it means that I'm going to approximate a derivative that I know is the variation of the function around x at the iteration n, so around x here. Now, numerically, the delta x is in fact becoming a variation of x. And then I can decide that either I'm making a perturbation in only one direction. So it means I'm at the function xn of xn. I'm making a perturbation to the x. So now I'm going to calculate the new function at x plus delta x. And I will have a new value that needs to be calculated for the function. And I can declare that the derivative is the difference of the functions divided by the variation of x. Okay? So first, it's approximation of the derivative. If I want to be a little bit more precise, what I can do is that I can say that I'm at xn. So if I want to make a perturbation around xn, it would be better to do it by decreasing the value of x and increasing the value of x. So xn is a central point, but now I'm going to do minus delta x over 2 and plus delta x over 2, so that the full variation is delta x. Okay? Now I'm calculating, I need to do two functions evaluation. In this case, there was only one additional one. Here there are two functions evaluations, but you can see that the difference might be, so the way you will calculate the derivative will be quite different. So if I'm here and I want to know what is the slope, I do a step in this direction and then I have the blue slope. And if I'm doing the central one, minus x plus 2, x, half of x, half of delta x, and plus half of delta x, you can see that the slope, the red slope, is better approximating the slope of the derivative. Okay? But the price to pay is 2 function evaluation instead of 1. And it's possible that evaluating a function, you have seen that in the example that I've given to you, is an integral, so it's a long calculations, 8,700 hours of operation. Okay, if I want to have it on 1 year. Okay, so it means that it might cost a lot, and therefore we have to ask ourselves if we do this one or this one. And now we have to decide when we stop. And typically there are 2 types of stopping criteria. The first one is to say that the function that we would like to be equal to 0 has to be close to 0. Okay, so it means that I'm going to choose a small value which is representing close to 0, and I'm going to verify that the absolute value of the function, and the absolute value is that I'm as satisfied by minus 1 to the minus 6, or plus 1 to the minus 6. Okay? So it means that if the function is lower, the absolute value of the function is lower than the epsilon here, then I say that I declare that I am satisfied. Okay? Now it might happen that for a small difference here, there are a lot of x that are still valid. It means that the slope is very, very low. Okay? In this case, it makes sense to test also the variation of x. Okay? So it means that I'm going to verify that the x is still not varying. Okay? I'm using the same epsilon, and typically I'm going to assess this because I do not know what is the value of x, so it might be very big or very small. Okay? So typically we assess the variations with an absolute or a relative value. So it means that if the value is quite small, I'm going to test to compare it with 10 to the minus 6. But if the value is quite big, so enthalpy, for example, is 10,000, the typical order of magnitude, then what I'm going to say is that I would be happy if it varies only for x%. Okay? And this is the trick that is used here. So we have here the relative value that is used in order, and it should be in fact the also an absolute value here, which is applied to the epsilon. So it means that at the end, I will be happy if the x is not varying too much and if the function is sufficiently close to 0. So this is the convergence problem. Okay, so we have a very nice method that relies on one element. I have to choose the right initial point. Okay, so going back here, I need to start with a given point here. And this is also introducing the problematic of this method, because if I am in this situation, for example, and if I'm starting from this point here, from this point here, well, the function is quite special, but it's a quadratic, is a factor 3 exponent function. So as soon as the factor 3, the polynomial is and the factor 3 is negative, then you have a variation, a slope shape like this. Okay, and what you can see is that if you start from this point here, you apply the formula, you will go here, and then you will calculate this one. You apply the formula, and you go there, and you are dead. In fact, you are diverging. Okay, so it means that you have to be smart in choosing the initial point. Okay, and I would say that the method works always when you have, as an initial guess, the solution. Okay. Otherwise, there is a risk of divergence. If you have divergence, then there is a possibility of doing what we name a relaxation. So what we can always say is that instead of making the full step, so going from xn to xn plus 1, all the points in between xn and xn plus 1 are also going in the right direction of decreasing the function. Okay? So it means that I can decide not to do the full step, but to stop in the middle. So it means that I'm calculating the full step here, and I'm going to decide what we name a relaxation factor that is going to say, okay, the new value of x will be a combination of the previous value and the expected value if the system is 100% linear. Okay? And then we will test if we are improving in order to decide the value of Q. Okay? So, we test it by looking at the steps we obtain when we obtain we apply Q is equal 1. So it means Q equals 0, so no relaxation. We look at if we are approaching 0, which means that the linear approximation is good. Okay? And if then we realize that it is not the case, then we go in the middle and we check again. And by checking again, then it allows us to decide if we are having a function that is highly nonlinear or that can be easily approximated with the first order. Okay? So it means that at the end we can change and adapt during the iterations the value of the relaxation coefficient. Of course, we can also be smarter. Okay, and decide that instead of having the first order development, we can limit it to the second order. Okay, but then it would mean that we would have to calculate the second derivative or be smart. And when I'm saying be smart, is that we can observe the value of f with 3 points, and having the 3 points, we can calculate the 3 values, A, B, and C, just by solving explicitly the set of equations here. And as soon as I have A, B, and C, then I have an analytic formula that is going to give me the value of the new x. So that means that now I'm considering that the function is a quadratic instead of being a straight line, but it's possible that my problem is more a quadratic one than a straight line. So it's be smarter, but it requires more evaluation. If I'm applying this method, I can also use what we name the chord method. And the chord method is going to say, instead of having to calculate the derivative, so I'm in a point I have to make a perturbation and then recalculate the function. So what I can do is to say, okay, let's make a step and deduce what is the derivative of the straight line between the 2 points that I have calculated. And decide that this is the approximation of the slope. So if the problem is linear, solution is found. Okay? If the problem is nonlinear and if I have made a big step, then it's possible that my evaluation is completely wrong. Okay? But it allows me to have an approximation of the derivative without having to make perturbations. Okay? And this would then allow us to approximate to apply the Newton without losing time in evaluating the derivatives. Okay? So graphically it means that I'm here, I'm going to have another point here, and I would say that as soon as we realize that we are around 0 for the function, then the method of the chord is very nice, because so you say, I'm here, I go here, oops, I'm going from minus something to plus something. Then I'm going to say, okay, the slope can be approximated like this, and I will use the next point and bring this one. Continue with this one. Now I'm going to make from there to there, go here, and again until I'm reaching the zero. So based on the same concept, allowing to approximate the derivative in another way. If the problem is linear, then the two methods go at exactly the same speed, but you can see that in this case, the chord method would have led me to this point here, while if I would have calculated the slope at this point, I would come here. So it means that the results will be a little bit different. Okay? Or the list of iterations will be different. Okay? In the case where you have explicit formulations, so x is the function of x that you would like to solve, well, there is an easy way, is to transform this equation into x minus f of x equals 0, and then you have a method that allows to solve the problem directly. But on the other hand, there is another way of doing it, is to say that if I have x that is a function of x, then what I can say is that the new x is the value of the function from the previous x. Okay, so it's a substitution mechanism. Okay, substitution mechanism is very dangerous in MATLAB. Okay, because you can write in MATLAB a equal a function of a, because it's a variable and it takes the content of the in the memory of the previous value. Okay. The problem, if you do it in MATLAB, is that you will never test if you have converged or not. For me, you will never know if A of the new iteration is similar to the A of the previous iteration. Okay, so it means that you need to add the convergence test to be sure that you are not just hoping that everything goes well. And I can tell you that this can create very big problems when the functions are highly nonlinear. Okay? So, and one of the reasons why I'm saying this is that, okay, you can converge like this one, so you go progressively. So the bisectrice is x, the function is this line here, and you are looking for the intersection of the two. Okay? And you can see that you start from x, you calculate f of x, so the new value of f is this x1, then you go to the new value of f, and then it converges quite nicely. Okay? But it can also diverge. Okay? So it means that if you do not test the convergence, then the system will never find a solution. Okay? And it can converge in different ways. So it can turn around or diverge progressively by turning around or by oscillating. So very important here, not be trapped by an error. So the substitution is quite nice. It does not need a lot of actions because you just calculate functions and then make a substitution, but don't forget to test. Okay? Otherwise, you will have a problem. And when you test, then you can identify if you are going to diverge. So it means that you are always allowed to say that I'm only going to make the half of the step. Okay? So the relaxation works as well with this kind of methods. And there is also a chord method for the explicit scheme, which is going to say that, so in fact, what I need to do is to find the intersection between this line and this one, okay? this is a straight line and this is a curved line. And what I can always do is that I can always say that instead of just doing a substitution, is that by using those 2 points, I can calculate the new one here. And then go very fast to this point here. Okay, it means that I'm approximating the slope by a straight line that is calculated between 2 points that I have made. So I know that if this slope is approximated by this straight line, the new x should be here, then I'm going here, and I will be able to to converge by making those points here, to converge to this point here. Okay, quite fast. Yeah, this is for the one variable, one equation. In reality, you will be facing the problem of 10,000 equations and 1,000 variables. Okay, so how we do we do this when we have more than one variable? Indeed, what we are going to do is that we are going to apply exactly the same principle, because the Taylor expansion works in multi-dimension. Okay, so what I'm going to do is that I'm going to define an array of functions that needs to be set to 0 by fixing the value of the x. I'm going to consider that I have an initial guess, and I'm going to consider that the vector of the function is approximated by the first Taylor development. So it means the function at the initial point plus the sum, but now it's a matrix, of the derivative of the function I with respect to the variable g, okay, that I will multiply by the variation of g. And if I have this, then I will be able to calculate, so it's really a matrix definition. So it means that I need to calculate all the derivatives of each of the functions with respect to each of the variable, okay, by perturbations, but it means calculate a lot of variations, okay? Then I will have to invert matrix here in such a way that I will be able to give you the value of the next step, knowing the value of the first step, by having the inverse of the matrix and the initial value of the functions that we expect to be equal to 0. Okay? So the formula is exactly the same, except that now I have to invert the matrix, and I have to apply, and I have to multiply matrices, and I have to calculate the Jacobian matrix, which is the matrix of the derivatives. Okay, so it means time to be spent in calculating the variations, right? And then we will have to test the convergence, and in this case, the test of convergence will just have to consider the norm of the vector. It means that I'm not going to consider only one value, but the norm of the whole vector of all the variables that needs to be lower than a certain epsilon, and the same for the variations on the variables here. Okay. One of the difficulties of this is that it's possible that in the same problem, I will have variables that are at the order of magnitude of 0.1 and others, like flow rates, for example. And then afterwards, in the same set of variables, a temperature at the value of 100 and an enthalpy at the value of 1000 order of magnitude. So it means that in this case, I will have a problem in the comparison here, because everyone will be compared with respect to one epsilon and a single one. Okay? So it means that I need to do something which is to use a mathematical trick in such a way that I will be satisfied with the definition of my epsilon for all the variables and all the functions. And the trick is to use scaling. I'm going to define a scaling factor that will apply to all the functions in such a way that if I'm comparing the value of one of the functions to e to the minus 6, I will be satisfied. Okay, so it means that I'm going to apply a multiplication factor in front of the function, the real value of the function here, and I'm applying a multiplication factor so that it can be compared to epsilon. And the same for all the variables. I'm going to apply a multiplication factor to all the variables in such a way that in my numerical procedure, in my algorithm, everyone will be seen with the same order of magnitude and can be compared to the same epsilon. Okay? So this is the scaling factor which allows us to then really make the comparison with the same value. So the Newton-Raphson approach has the same conditions as in multi-dimensional than we have in the single dimension. It means that we need a good initial guess. And if it appears that we are diverging, so it means that the norm of the f of x is increasing, then we are not forced to do the full step. We can always do a partial step. Okay? And in this case, we will apply a relaxation factor so that the new one will not be the full step, but will be somewhere in between, but in the direction that I have calculated from the derivatives. Okay? So calculating derivatives takes time, and so it means that we will not do central derivatives. Most of the time we just choose a direction for evaluating the derivative. It's just an approximation. If we have big problems, so what we will do also is that we will try to reuse the direction. So it means that instead of recalculating the derivative, we take the previous one that we have already inverted, and then we make several steps with the same slope, and hope that it will give us the good directions, even if the problem is nonlinear. And if the functions are complex and are including iterative processes, because nothing is telling us that during the calculations we have not also solved a sub-problem which is using iterations. It makes sense also to test the numerical noise. The numerical noise is calculated in this way. So you make perturbations on x, on all the x, you calculate functions for all the perturbations, and you recalculate the original value. If there is a difference between the original value and the last one that you calculate for the same value of x, it means that there are some noise in the calculation. And if this noise is higher than the value that you are observing here, then you have a problem, because it means that you are measuring a derivative that is in fact in the noise. Okay? And in this case, it would mean that we would have to increase the value of the perturbation here to be sure that the slope is a real slope. Okay? Right. So I'm going to end here to just remind you that the principle of solving a nonlinear equation, or a set of nonlinear equations requires an initial guess. And something which is important for engineers is that typically they know quite well where will be the answer. We do not know exactly the value, but at least the order of magnitude. So it means that the knowledge of engineers is important to have the right value for the as an initial value. And from there, then we can apply the derivatives and do the iterations to find the solution. So this afternoon at 1 o'clock, we convene here. Alessio and Tibi are going to make presentations on the first part of the problem, which is to identify the value of kth and ksun for the different buildings that we will have in EFL. So come back here at 1 o'clock.